From cosmic dust to living planet, Earth's violent birth and the spark of life. 2. Hook and intro. Look around you. At the vibrant blue sky, the lush green landscapes, the teeming life that surrounds us. It all feels so permanent, so natural. But what if I told you that this paradise was once a hellscape? A molten, uninhabitable ball of fire, constantly bombarded by celestial debris, with no trace of the air we breathe or the water we drink. What if I told you that the very existence of life on Earth is the result of a series of cosmic accidents, violent collisions, and a revolution powered by microscopic organisms that literally changed the planet's breath? The story we are about to uncover is not just a tale of geology and chemistry. It is the ultimate origin story, a cosmic drama spanning billions of years, full of fire, ice, and the improbable miracle of life. Our journey begins not with a whimper, but with a bang, a colossal impact that fundamentally shaped our world and gave birth to our constant companion in the night sky. Imagine a world forming in the vast, dark emptiness of space, a world that would eventually become our home. But before it could nurture life, it had to survive a childhood of unimaginable violence. For billions of years, Earth was a planet in flux, a dynamic crucible where every element, every atom, fought for its place. This period of intense transformation, from a desolate rock to a vibrant world, is the most pivotal chapter in Earth's history, a chapter that laid the very foundation for everything that has ever lived. Today, we will travel back in time, further back than any recorded history, to witness the chaotic birth of our planet and the miraculous spark that ignited life itself. We will explore the cosmic ballet of dust and gas that coalesced into a molten sphere, the cataclysmic collision that gifted us our moon, and the ceaseless geological forces that carved out continents and filled vast basins with water. We will then dive into the primordial oceans, a chemical soup teeming with possibility, where the first self-replicating molecules began an evolutionary dance that would change the planet forever. This is the story of abiogenesis, the profound mystery of how non-living matter gave rise to the first living organisms, and how these simple beginnings set off a chain reaction that continues to shape our world even today. The emergence of life was not a gentle unfolding. It was a battle against extreme conditions, a persistent struggle against a hostile environment. From anaerobic microbes clinging to existence in deep-sea vents to cyanobacteria performing a planetary-scale act of terraforming, every step in this grand narrative was a monumental achievement. This is not just dry scientific fact. It is an epic saga of survival, adaptation, and unforeseen consequences. You will discover how life itself, once established, began to fundamentally alter the very planet it inhabited, transforming its atmosphere and oceans in a way that would pave the path for all complex life forms that followed. This story is crucial because it helps us understand our place in the cosmos. It reveals the intricate dance between geological processes and biological evolution, a codependent relationship that has defined Earth for eons. By understanding how life arose and transformed our planet, we gain profound insights into the conditions necessary for life elsewhere in the universe, fueling the ongoing search for extraterrestrial existence. It also underscores the incredible resilience of life and the delicate balance of our planet's systems, offering vital lessons for our future. Prepare to witness the greatest story ever told, the genesis of Earth and the dawn of life. 3. Historical context and set up our story begins in the vast, cold emptiness of space, approximately 9.2 billion years after the Big Bang, a staggering 4.6 billion years ago. The universe, though ancient, was still birthing new stars and planetary systems. Our own solar system was just a nascent idea, a swirling cloud of interstellar gas and dust left over from the explosion of long-dead stars. This isn't just any dust, it's cosmic stardust, rich with the heavy elements forged in the hearts of supernova elements like carbon, oxygen, iron, and silicon, the very building blocks of planets, and eventually of life itself. Within this colossal cloud, a localized region began to collapse under its own gravity. This wasn't a sudden event, but a gradual tightening, pulling more and more material towards its center. As this cloud spun, it flattened into a colossal, rotating disk, much like a cosmic pizza. At the very heart of this disk, where the pressure and temperature became immense, our sun ignited, a blazing furnace of nuclear fusion, radiating immense heat and light into its surroundings. The remaining material in this protoplanetary disk continued its cosmic dance. Billions upon billions of tiny dust and gas particles, ranging from microscopic grains to pebbles, orbited the young sun. Over millions of years, these particles began to collide, not always violently, but often gently, sticking together through electrostatic forces. This process, known as accretion, was the fundamental mechanism by which planets are built. Like snowballs rolling down a hill, these small clumps grew larger, gradually forming kilometer-sized planetesimals. The early solar system was a truly chaotic place, a cosmic demolition derby. These growing planetesimals frequently crashed into each other. Some collisions were gentle mergers, allowing bodies to grow, others were destructive, shattering nascent worlds back into fragments. Yet, through this violence, certain bodies gained enough mass to become protoplanets, planetary embryos, hundreds or thousands of kilometers in diameter, gravitationally dominating their orbital paths. These were the true architects of our solar system, competing, colliding, and ultimately determining the fate of our early Earth. Our nascent Earth was one such protoplanet, growing steadily through this process of accretion. As it gathered more and more material, its internal temperature began to rise dramatically, fueled by the kinetic energy of countless impacts and the radioactive decay of elements within its core. This internal heat was so intense that the entire planet became a molten, fiery ball, a sphere of incandescent rock and metal. This early, hellish phase of Earth's existence is known as the Hadean Eon, a name derived from Hades, the Greek god of the underworld, a fitting description for a world of fire and brimstone. The early Earth was a dynamic entity, its interior undergoing a process called differentiation. Because it was molten, denser elements, primarily iron and nickel, sank towards the center under the relentless pull of gravity, forming the planet's core. Lighter silicate materials rose to form the mantle, and eventually a thin, unstable crust. This internal convection, the movement of molten material, was incredibly vigorous, driving intense volcanic activity across the surface. This primordial Earth was a planet without respite, a constant spectacle of fiery eruptions and seismic tremors. Even in this violent infancy, certain elements were already in play that would prove critical for life. Water vapor was being outgassed from Earth's interior through volcanoes, along with other gases like carbon dioxide, methane, and ammonia, forming a primitive, anoxic atmosphere. This early atmosphere, devoid of free oxygen, was vastly different from the one we breathe today, a toxic brew for any oxygen-dependent life. But it contained the raw ingredients, the simple molecules, that would eventually be rearranged into something far more complex. Then, approximately 100 million years after Earth's initial formation, around 4.5 billion years ago, a truly cataclysmic event unfolded. A Mars-sized protoplanet, now known as Theia, was on a collision course with our young Earth. This wasn't a glancing blow, but a direct, head-on impact of unimaginable force. The consequences of this single event were so profound that they reverberate through every aspect of our planet's existence, from its rotation to its magnetic field, and crucially, to the very presence of our moon. This was the moment when Earth truly began to take its destined shape, albeit through an act of cosmic violence. 4. The story unfolds Phase 1. The cosmic hammer blow and its aftermath, the collision with Theia, was not merely an impact. It was an act of planetary reshaping. When Theia slammed into Proto-Earth, the force was so immense that both bodies were largely vaporized, their material ejected into a colossal ring of superheated debris orbiting the Earth. This debris, over a relatively short period of time, perhaps only a few centuries or millennia, began to coalesce under its own gravity, forming the Moon. Our constant celestial companion, the source of our tides and a stabilizer of our axial tilt, was born from this singular, devastating event. The Moon itself is largely composed of material from Earth's mantle and Theia, a silent testament to the greatest collision in our planet's history. But the impact did more than just create the Moon. It was the final, defining act in the formation of Earth's iron-nickel core. The sheer energy of the collision caused the materials within Earth to fully differentiate, with the densest components settling definitively into the core. This molten, metallic core became a dynamo, its convection generating a powerful magnetic field that would wrap around the planet, shielding its surface from the harsh solar winds and cosmic radiation. Without this protective magnetosphere, Earth would have been stripped of its atmosphere and water, rendering it utterly uninhabitable. Theia's violent embrace, paradoxically, secured Earth's long-term future. The impact also profoundly affected Earth's rotation. It tilted our planet's axis, giving us the stable seasons we experience today. This tilt, combined with the gravitational pull of the newly formed Moon, helped stabilize Earth's rotation, eventually settling into the roughly 24-hour day-night cycle. This consistent rhythm of light and dark, heat and cold, would prove crucial for the development of life, allowing for stable environmental conditions over vast periods. For hundreds of millions of years following this collision, the Earth remained a searing hot, geologically active world. This was the peak of the Hadean Eon, a period of relentless volcanism, with magma oceans still dominating much of the surface. As the surface gradually cooled, a thin, unstable crust began to form, only to be constantly recycled by intense tectonic activity and renewed volcanic eruptions. This was a planet still finding its footing, still solidifying its outer shell. Adding to the chaos was the late heavy bombardment, a period roughly between 4.1 and 3.8 billion years ago, during which the inner solar system was subjected to an intense barrage of asteroids and comets. The scars of this bombardment are still visible on the Moon's heavily cratered surface. On Earth, however, geological activity has largely erased these early impact craters. These impacts, while devastating, are also theorized to have delivered significant amounts of water and complex organic molecules to Earth, adding crucial ingredients to the planet's nascent chemical soup. Phase 2. The birth of oceans and the primordial soup. As Earth continued its slow, inexorable cooling, a critical transition began: the formation of its oceans. Water vapor, released from the planet's interior through billions of years of volcanic outgassing and potentially supplemented by icy comets and asteroids, gradually accumulated in the early atmosphere. As the surface temperature dropped below 100 degrees Celsius, this water vapor condensed, raining down upon the planet for millions of years. Imagine a perpetual global deluge, filling the deepest basins and carving out the first river systems on a cooling, rocky world. Around 4 billion years ago, the first stable liquid water oceans began to form. These weren't the serene blue oceans we know today. They were likely warm, acidic, and rich in dissolved minerals and metals, a true primordial soup. This aqueous environment was critical. Water is an extraordinary solvent, capable of dissolving and transporting a vast array of chemical compounds. It also provided a stable medium where molecules could interact, react, and accumulate over vast timescales, protected from the harsh UV radiation that still permeated the atmosphere. The early atmosphere, meanwhile, remained largely anoxic. It was a dense mixture of water vapor, carbon dioxide, methane, ammonia, and nitrogen. This reducing atmosphere, rich in hydrogen and lacking free oxygen, was precisely the environment needed for the spontaneous formation of complex organic molecules from simpler inorganic precursors. Lightning, volcanic activity, and UV radiation provided the abundant energy needed to drive these intricate chemical reactions. This was the stage for one of the greatest mysteries in science: abiogenesis, the origin of life from non-living matter. Scientists hypothesize that in these primordial oceans, or perhaps in the protected environments of deep-sea hydrothermal vents, simple inorganic molecules began to react, forming more complex organic compounds like amino acids, nucleotides, and fatty acids. These were the basic building blocks of life, accumulating in the soup. Then came the next crucial step: the polymerization of these building blocks into longer chains. Amino acids linked to form proteins, and nucleotides joined to form nucleic acids. The RNA world hypothesis suggests that RNA, not DNA, was the primary genetic material of early life. RNA has a unique dual capability. It can store genetic information, much like DNA, but it can also catalyze chemical reactions, like proteins. This made it a perfect candidate for the first self-replicating molecule, a true proto-life form. The final critical step in this chemical evolution was encapsulation. These self-replicating molecules needed to be separated from their external environment to maintain a stable internal chemistry. Lipid molecules spontaneously formed membranes, creating tiny, enclosed compartments, protocells. These primitive cells were the precursors to all life, capable of carrying out basic metabolic reactions and, crucially, of passing on their genetic information to offspring. Phase 3. The reign of microbes and the Oxygen Revolution. Around 3.8 to 3.5 billion years ago, the first true life forms, prokaryotes, emerged. These were simple, single-celled organisms, lacking a nucleus and other membrane-bound organelles. They were anaerobic, meaning they thrived in the absence of oxygen, metabolizing chemicals from their environment for energy. They were the masters of their domain, populating the nascent oceans in immense numbers, a thriving microbial world hidden beneath the waves. For over 1 billion years, these anaerobic life forms dominated Earth. They were the planet's first engineers, slowly but surely altering their immediate environments. One of the most significant innovations in the history of life was the development of photosynthesis, the ability to convert sunlight into energy. Early forms of photosynthesis, known as anexigenic photosynthesis, did not produce oxygen. They used other electron donors like sulfur compounds. Then, around 3.5 to 2.5 billion years ago, a group of remarkable organisms emerged. Cyanobacteria. These blue-green algae evolved a revolutionary new form of photosynthesis, oxygenic photosynthesis. This process used readily available water as an electron source, releasing molecular oxygen, O2, as a byproduct. This was a game changer, not just for life, but for the entire planet. Initially, the oxygen produced by cyanobacteria did not accumulate in the atmosphere. Instead, it reacted with the abundant dissolved iron in the oceans, precipitating out of the water to form massive geological deposits known as banded iron formations (BIFs). These distinctive red and black striped rocks are found all over the world and are direct evidence of Earth's first global-scale environmental engineering project. For hundreds of millions of years, the oceans acted as a vast oxygen sink, slowly removing iron from the water and storing the oxygen in solid rock. But eventually, the oceans became saturated with oxygen. The iron ran out, and free oxygen began to escape into the atmosphere. This marked the beginning of the Great Oxidation Event, GO, also known as the Oxygen Catastrophe, starting around 2.4 billion years ago. This was an environmental revolution on an unprecedented scale, transforming Earth's atmosphere from anoxic to oxygen-rich over millions of years. The planet began to breathe differently, and the consequences were profound and immediate. Phase 4, the Oxygen Catastrophe and the path to complexity for the anaerobic life forms that had thrived in an oxygen-free world. The rising levels of oxygen were a deadly poison. Oxygen is a highly reactive molecule, and for organisms not adapted to it, it caused widespread cellular damage. The GOE likely triggered one of Earth's first and most devastating mass extinctions, wiping out countless species of anaerobic microbes. Life had inadvertently engineered its own environmental crisis, a testament to its power to shape the planet. However, for some organisms, oxygen was not a killer but an opportunity. New forms of life began to evolve that could not only tolerate oxygen, but also harness its reactive power for energy. Aerobic respiration, which utilizes oxygen to extract far more energy from food than anaerobic processes, became possible. This was a crucial evolutionary leap, providing organisms with a vastly more efficient way to fuel their growth and activity. The presence of abundant energy would be a prerequisite for the evolution of more complex life forms. The accumulation of oxygen also had another critical long-term effect: the formation of the ozone layer. As oxygen rose higher into the atmosphere, it reacted with UV radiation to form O3, ozone. This ozone layer acted as a protective shield, absorbing much of the harmful UV radiation from the sun. Before the ozone layer, the surface of Earth was constantly bombarded by sterilizing radiation, limiting life to the depths of the oceans or beneath protective rocks. With the ozone layer, shallow waters and eventually even land surfaces became potentially habitable. Around 2 billion years ago, another monumental evolutionary event occurred: the emergence of eukaryotic cells. These cells were far more complex than prokaryotes, possessing a nucleus that housed their genetic material and other specialized, membrane-bound organelles like mitochondria and chloroplasts. The prevailing theory for their origin is endosymbiosis, where one prokaryotic cell engulfed another, forming a symbiotic relationship where the engulfed cell became an organelle. Mitochondria, the powerhouses of eukaryotic cells, are believed to have originated from engulfed aerobic bacteria, while chloroplasts in plant cells came from engulfed cyanobacteria. The rise of eukaryotes, with their increased genetic capacity and metabolic efficiency, set the stage for further complexity. Around 1 billion years ago, the first multicellular organisms began to appear. Cells, instead of living independently, started to cooperate, specializing in different tasks and forming larger, more intricate structures. This was a radical departure, paving the way for the vast diversity of plants, animals, and fungi we see today. The journey from a molten rock to a planet teeming with eukaryotic, multicellular life was a process of continuous transformation, marked by periods of immense change and seemingly impossible innovations. The Great Oxidation Event and the subsequent evolution of eukaryotes fundamentally altered the trajectory of life on Earth, creating an environment where complex organisms could not only survive but thrive. These early microscopic organisms, through their profound influence on planetary chemistry, truly engineered the world, laying the groundwork for the Cambrian explosion and all the incredible biodiversity that would follow. 5. Impact and legacy. The impact of Earth's formation and the subsequent emergence of life cannot be overstated. It is the foundational narrative for everything that has come after. The immediate consequence of the Great Oxidation Event, driven by cyanobacteria, was a radical shift in Earth's atmospheric composition. For billions of years, the atmosphere had been rich in reducing gases, but now it became oxygenated. This change was lethal for much of the existing anaerobic life, but it opened a vast new frontier for organisms that could utilize oxygen. It transformed a world that smelled of sulfur and methane into one where oxygen-breathing life could flourish. The long-term legacy of this oxygen revolution is profound. The development of aerobic respiration provided a far more efficient energy pathway, enabling the evolution of larger, more energetic, and more complex organisms. Without the massive energy yields provided by oxygen, the intricate machinery of multicellularity, advanced nervous systems, and eventually intelligence would simply not have been possible. Every animal, including humans, relies on the legacy of these ancient microbes and their transformative power. Our very metabolism is a direct descendant of the evolutionary adaptations forged during the Great Oxidation Event. Furthermore, the formation of the ozone layer, a direct result of atmospheric oxygenation, was a critical step in making terrestrial environments habitable. Before ozone, the land surface was a barren, UV-blasted wasteland. The protective shield of ozone allowed life to eventually venture out of the oceans, colonizing continents and driving further diversification. This land colonization, starting with primitive plants and fungi, eventually led to the development of complex terrestrial ecosystems, fundamentally altering Earth's geology through processes like soil formation and weathering. Imagine an alternate history. What if Theia had missed Earth? We might not have a moon, resulting in a wildly unstable axial tilt and chaotic climate swings, making sustained life incredibly difficult. What if abiogenesis had never occurred, or if oxygenic photosynthesis had never evolved? Earth would likely remain a world dominated by anaerobic microbes, a static planet without the dynamic interplay of complex ecosystems, never witnessing the rise of biodiversity we see today. These counterfactuals highlight the fragile, contingent nature of our planet's history and the precious uniqueness of its life. The story of Earth's formation and the origin of life is also inextricably linked to the ongoing search for extraterrestrial life. By understanding the specific sequence of events on Earth, the role of liquid water, a protective magnetic field, suitable atmospheric conditions, and the capacity for self-replicating molecules, scientists can better identify potentially habitable exoplanets. The discovery of extremophiles on Earth, organisms thriving in conditions once thought impossible, also expands our definition of what life might look like elsewhere, guiding the search beyond our terrestrial biases. The entire tree of life on Earth traces its lineage back to those earliest protocells, to the last universal common ancestor, Luca. Every living thing, from the smallest bacterium to the largest whale, is part of this unbroken chain of inheritance, a testament to the power of evolution and the interconnectedness of all biological processes. This fundamental connection underscores the unity of life, reminding us that we are all distant cousins, sharing a common origin in the primordial soup. The geological and biological forces that shaped Earth are not merely historical footnotes, they are ongoing processes. Plate tectonics continues to reshape continents, volcanoes still spew new material, and life continues to influence global cycles of carbon, oxygen, and nitrogen. This dynamic interplay means that Earth is not a static stage for life, but an active participant, constantly evolving and responding to the myriad forms of life it harbors. The planet and its life are in a perpetual dance of co-evolution. 6. Reflections and lessons. The journey from cosmic dust to a living planet offers profound insights into the nature of existence itself. It teaches us about the immense power of physical forces, the incredible resilience of simple chemistry, and the astonishing capacity for life to emerge, adapt, and transform its environment. One of the most striking lessons is the sheer timescale involved. Billions of years passed before complex life arose, a humbling reminder of the patience of the cosmos and the slow, incremental nature of profound change. The story of Earth and life also highlights the delicate balance and intricate interdependencies within a planetary system. The formation of the magnetic field, the presence of liquid water, the perfect distance from the Sun, each of these factors was critical. A slight variation in any one of them could have rendered our planet sterile. This fragility should make us deeply appreciate the rare conditions that allowed us to exist. We also learn about the power of life itself as a geological force. The Great Oxidation Event demonstrates that even the simplest organisms, over vast periods, can profoundly engineer a planet's entire atmosphere and ocean chemistry. Life isn't just a passenger on Earth, it's a driver of planetary change. This historical precedent is particularly relevant today, as humanity, through its own actions, is causing rapid and dramatic changes to Earth's climate and ecosystems. What lessons can we draw from the ancient cyanobacteria? Consider these questions. How would our understanding of life and our place in the universe change if we were to discover another planet with a similar oxygen-rich atmosphere, but without any complex life forms? What does the oxygen catastrophe teach us about the unintended consequences of revolutionary biological or technological advancements? Could our own innovations lead to similar, unforeseen environmental crises for existing life? Given the immense time it took for complex life to evolve on Earth, how might this impact our expectations for finding advanced civilizations elsewhere in the cosmos? Are we simply an anomaly, or is this a common trajectory? If the conditions for abiogenesis are likely to be found in environments like deep-sea hydrothermal vents, what does this tell us about the resilience and adaptability of life at its most fundamental level? How does the story of Earth's violent birth and the gradual emergence of life influence your perspective on the concept of home and the preciousness of our planet? The fact that all life shares a last universal common ancestor suggests a deep unity. How can this understanding foster a greater sense of stewardship for biodiversity and ecological preservation? These questions remind us that history, even planetary history, is not just a collection of facts, but a source of profound lessons that continue to resonate in our present and future. 7. Outro: the incredible odyssey of Earth, from a swirling cloud of cosmic dust to a vibrant, living planet, is a testament to the immense power of time, chance, and the relentless march of evolution. We have witnessed the cataclysmic birth of our moon, the fiery crucible of the Hadean Eon, and the relentless rains that formed our primordial oceans. We dove into the mystery of abiogenesis, the moment when non-living matter stirred into life, setting off an unbroken chain of biological innovation. And we explored the revolutionary impact of cyanobacteria, whose ancient breath transformed Earth's atmosphere, paving the way for the incredible complexity we see today. This grand narrative is far from over. The story of Earth and life continues to unfold, driven by the same geological and biological forces that have shaped it for billions of years. If you found this journey through deep time captivating, you might also be interested in other pivotal moments in Earth's and life's history. Consider exploring the Cambrian explosion, the spectacular diversification of complex, multicellular life forms that rapidly appeared around 541 million years ago, filling the oceans with a bewildering array of creatures. This event truly launched the era of visible life on Earth. The age of dinosaurs and mass extinctions, the reign of colossal reptiles, and the series of devastating mass extinction events, including the one that wiped out the dinosaurs, profoundly shaping the course of evolution and creating opportunities for new forms of life to flourish. The evolution of humanity, the long and intricate journey of our own species, Homo sapiens, from our earliest ancestors in Africa to our global presence today, a story intertwined with climate change, technological innovation, and societal development. The search for extraterrestrial life, beyond Earth, the ongoing scientific quest to find life on other planets and moons in our solar system, and beyond, informed by our understanding of life's origins and resilience on our home world. The history of Earth and life is not merely a collection of past events. It is a dynamic, ongoing saga that continually shapes our present and future. By understanding where we came from, we can better appreciate the preciousness of our world and our unique place within the vast, indifferent cosmos. It reminds us that we are all products of cosmic dust and an improbable spark, part of a story far grander than we can ever fully comprehend. Thank you for joining us on this incredible journey through time.